And let me take you to the practice quiz for today. And I trust you all got the announcement, saw the announcement that I was up in Michigan. Thus, there was no class on Thursday. I was saying my goodbyes to my mother. She's still around, but the doc thinks that this will be her very last week.
I don't like.
Okay, so practice quiz.
Mr. Shankin,
Yes.
with everything that's going on with your mother, what does that mean for our class? Because obviously you will be involved in things taking care of her death if she does die this week, and her funeral and everything. If that's okay for me to ask.
Good question.
I mean to cry it off.
Yeah. I've posted a new schedule. So I shifted, and it includes that we had the day off. And I moved the due dates down, and I removed a section out of the schedule. So I've compensated for the day that we missed. I'm not going to be missing any more days because in these COVID times, the funeral is going to be kind of a Zoom thing. So I'm not going to be missing any classes. That's why it was more important to me to go and say my last goodbyes to her, see her while she's still around. So it shouldn't disrupt the class anymore.
Okay, thank you.
You're welcome.
And one more thing. I also noticed, so December 10th is supposed to be our last day.
Mm-hmm.
I noticed that it didn't look on my end that there was a final or anything, but just some add-ons and homework due then. Does that mean we don't have like an official exam for a final?
Oh, we do have a final exam. And it's
okay.
On Thursday, December 10th. That's in the schedule. Let me put a note to make sure that you can see it in the modules. I'll do that.
I probably just wasn't paying attention.
Okay. All right, so let me give you another minute here on this one. And 30 seconds more. Okay, so I'm going to write polynomial function for this. Something, but what degree should it be, and what's the least possible degree for this? Well, let's look at how many x-intercepts it's got. 1, 2, 3, 4, 5, 6 x-intercepts. So when I write these things out, x minus, let's say, the first x-intercept. And then there's x minus the second x-intercept, and so on. And we counted 1, 2, 3, 4, 5, 6, 6 of these. So this has got to be at least a 6th degree. The least possible degree is 6. Now there's another way I could have looked at it as well. Turning points. This was decreasing and then it's increasing. So we can call that a turning point. 1, 2, 3, 4, 5 turning points. And then that means it's got to be at least a 6th degree, because the number of turning points, maximum number of turning points, is 1 less than the degree of the polynomial. Alright, let's go to the next one. It's state the least degree of this one. Least possible degree. So again, let me show the directions of this. Give the least possible degree of that. Okay, 30 seconds more. All right, let me stop. All right, now, by the way, on this first one, we said the least possible degree was 6. Remember, with the degree of 6, that the end behavior would be either both up or both down. And it was both up, and that was consistent. On this one, my first instinct might be to say, well, there's 3 x-intercepts, so it's going to be degree 3. But I immediately run into a problem. Degree 3, if it was up on the right, it would be left on the down on the left. Or if it's left on the right, up on the left, and it's down on the right. The end behavior doesn't match for degree 3. How come it doesn't match? It's because right in here we touch. All the other ones have been crossing the x-intercept. But this one is a touch. When you touch, that means the multiplicity x minus 2, that's got to be part of this y function. But it's got to be to an even power. Like 2 or something like this. And so, it's not degree 3. The least possible degree is degree 4. And now it matches with the end behavior, both of them pointing in the same direction, either both up or both down. Also, if you count the number of turning points, bottom of a valley, top of a hill, bottom of a valley. 3 turning points. One more than that is the least possible degree, 4th degree polynomial. Alright, so give me a little feedback on A and number 1, A and B. Okay, and determine the end behavior of each of the following polynomial functions. Your choices for answers are below. You can say for A, up on the far left, up on the far right, B, down on the far left, down on the far right, C, down on the far left, up on the far right, D up in the far left, down in the far right. Okay, so choose A through D for each of the two for the end behavior. All right, 30 seconds more. So on number 1, the end behavior is on the far right it's going up, far left it's going down. That is choice down in the far left, up in the far right. This is choice C. And number 2, the end behavior totally determined by the leading coefficient, both of them down, down and far left, down and far right. So this is choice B. All right, give me a little feedback on number 2, please. State the distance and midpoint formulas. So don't look them up from memory. Okay, so let me give you 30 seconds more. Okay, both of these formulas depend on that there's a first point called x1, y1, and a second point called x2, y2. And then we have a line segment between them. And then one of these is going to tell you what the midpoint is, and the other one's going to tell you the distance d between these two. And d is equal to the square root of the difference of x2 minus x1. Difference in the x's squared plus the difference in the y's squared. And the reason for that is because this point is x1 over. This one is x2 over. And then the length of this is x2 minus x1. So that's the Pythagorean theorem. This side squared plus this side, that's the difference in the y coordinates. That squared is equal to that one. And the midpoint formula, m, midpoint is you average, add them up, divide by 2 for both the x and the y. Okay, and give me a little feedback on number 3. And as time has gone on, I'm realizing I've been trying all these different, feedback mechanisms, and maybe the best was without any numbers or without anything. It was just people just gave feedback on the quality of the review. So however you want to give feedback is fine. Any method is fine. And start with A, find that logarithm. I'll give you a brief 30 seconds. All right, this one, you ask the question, what is the exponent you place on top of 2 to get 8? And that exponent is 3. The logarithm is the exponent that goes on top of that base to get that result. And then do part B. Thirty seconds more. This one might seem mystifying at first. 8 to what power is 2? Well, if you take the cube root of 8, but the cube root of 8 is the same as to the 1/3 power. 8 to the 1/3, if you recall, that number comes out. These are warring. The top number is trying to make the 8 bigger. The bottom number is trying to make it smaller. And the bottom number is bigger, so it wins the war. And it makes the whole thing smaller. Hold on. Cube. So 8 to the 1/3 is 2, but the answer is not 2. It's the power that you had to raise the 8 to get 2. So although this is kind of a check of my work, still the answer is 1/3. Okay, a little feedback on A and B. Okay, go to C and D. 30 seconds more. Okay, so this is saying 4 to what power is 1/4? That's what negative exponents do. Brings it down to the denominator. This one is asking 9 to what power? It's going to give me 3. 9 to the 1/2, that's the same as the square root. Okay. And let's go to the next two, E and F. Thirty seconds more. Okay, 2, if I raise 2 to the 2 power, I get the 4. But if I raise 2 to a negative 2 power, not only do I get a 4, but the negative slams it into the denominator. And so I'm going to get 1/4. And then 2 to what power, if I ask the question, 2 to what power gives me a result of 2 to the 5th? The answer is 5. Because it's 2 to what power is equal to 2 to the 5th. So the question mark and the 5 have to be the same thing. Okay. Give me a little feedback on these last 4. And do G and H. Thirty seconds more. Okay, on this one, I'm just going to do what? I'm going to circle. I'm going to do that first. Log base 3 of 9 asks 3 to what power is 9, and that's 2. 3 to the second power is 9. Now I raise 3 to the second, and I get 9. H. The problem is I can't do this part first. 3 to what power is 17, I can't figure that out. It's going to be something between 2 and 3, because 3 to the second is 9, that's too small. 3 to the third is 27, that's too big. It's somewhere between 2 and 3, but I'm going to raise 3 to this power. So what I'm going to do, instead of focusing on figuring out that, This is one where we really need to rely on the inverse relationship. Exponential with base 3 and logarithm with base 3 are what we call inverse functions. And since they're inverse functions, they kill each other off. And what I'm going to get is 17. And in fact, this could have been done in the previous ones. Let's look. 3 and log base 3. 3 to a base, exponential function with base 3, logarithmic function with base 3, kill each other off, we get 9. We could have done it that way. Log base 2, an exponential function with base 2, kill each other off. We could have done this one that way as well. These two are inverses of each other, so back to back, they kill each other off. Like, start with 11 and add 5 to it and subtract 5 to it. Then you get back to 11. So adding 5 and subtracting 5 are inverse. They kill each other off, same as these things. Logarithm was created to be the inverse function of the exponential function. It undoes it. All right, a little feedback on G and H. Sketch the graph of y equals 2 to the x power. So, quick graph. Give you just a quick 30 seconds. If you remember the rough shape. Okay, so an exponential function like this always goes through 1. It's important we label that. Now, where does it hit the y-axis? At 1. And to the left, takes a long time, slowly getting larger. And then to the right of it, it goes up quickly. So just like y equals x squared, we know we could draw a quick little parabola. We need the same kind of familiarity with exponential functions to say, oh yeah, it becomes this thing. And real quick review of why it is. When you put 0 in there, anything to the 0 is 1. That's why we always get this point. Hits the y-axis at 1. When you put 1 in there, you get 2. 2 in there, 2, the second is 4, and then 8. You can see why it's going up on that side. Why it's going on the left side. You see, you get smaller and smaller fractions. That's why it goes down. All right. A little feedback on number 5, please. All right. And while we're doing this, I realized I need to do a few more. And let me just write these in. Now, number 6, using calculator. A, find the log of 6. B, do the ln of 8. C, do the log of -3. And D, do the log base 3 of 7. Okay, 30 seconds more. Okay, this first one, the unwritten base is 10. When you plug it into your calculator, well, and the unwritten base over here is E. Over here is 10 again. Okay. You punch these into your calculator, and it knows it's base 10. And when I punch this first one in, I get approximately, put a wiggly equal at the top, approximately 0.77815. Okay. And ln of 8 is approximately 2.0794. Okay, and after this, things should have gotten difficult for you. If I take the log of -3 in my calculator tells me error. Some way your calculator will convey to you some error was made. And this makes total sense, because let's call it x for a minute. 10 to some power, base to a power, it's got to give you the result of -3. But when you raise 10 to a positive power, you always get a positive answer. When you raise 10 to a negative power, you get a fractional answer, but it's still positive. This has no solution. That's why your calculator is giving you an error. You can't do this. So you can't put in negative numbers. You also can't put in 0 into a logarithm. 10 to some power being 0 is also impossible. And the last one, you should have had difficulties with, because most calculators only have these two bases available, base 10 and base E. So log base 3 of 7 is just not available to us in our calculator. This one we'd say that we can't do. 3 to what power is going to give me 7? We can't do yet. Today we're going to learn how to do this kind of a problem with our calculator. And by the way, before we move on from this, take your calculators and check your work on A. Now how I want you to check is take 10, raise it to this power, and see if you get really close to 6. You won't get exactly 6 because you're, chopping off some decimals in there. So when I raise 10 to the 0.77815 power, I get 5.999, like 4 nines in a row before I get an 8. So this gives me really close to 6. And we can verify these answers with our calculator as well. All right, a little feedback on number 6. All right, and yeah, at first it kind of makes you feel like you're missing something. That was kind of what I was trying to evoke that feeling, like, oh my gosh, what did I miss? All right, now questions on any of the homework, anything else, any concepts?
Number 30th?
Number 30, and this is 6.3.
Yeah, it's for 6.3.
Okay. Log base 2 of x is equal to 6. And it says, for the following exercises, solve for x by converting the logarithm to an exponential form. So it says, convert to an exponential equation to solve. Alright, so we had learned that every logarithm equation can be written as an exponential equation. Every exponential equation can be written as a log equation. And we even had like a table, log equation, exponential equation. And you put the base to the exponent equals the result. So a log equation is always base result equals exponent. An exponential equation is base to the exponent equals result. So we just shifted it around. Base to the exponent equals the result right here. Thus, and then I just count on my fingers, my thumb being 2, and keep doubling it as I move to the next. 4, 8, 16, 32, 64. X is 64. Does that answer your question on 30?
Yes, I had another question, which was Sasha.
Sasha, okay.
I had a question on 36
Okay.
and 38.
Let's look at 36. So asking for log of 100 to the 8th. The unwritten base, whenever you write log, is 10. And now they're asking, what is the exponent you place on a 10 to get this? Well, there's a few different ways we could do this. A 100 to the 8th power could be written as 1 with how many zeros? Well, there's 2 zeros right here. When you raise 100 to the first, it keeps it 2 zeros. Raise 100 to the second, you just double the number of zeros. 100 times 100 is 10,001 with 4 zeros. 100 to the 8th is going to be 1 with 16 zeros. Because every time you multiply by 100, it adds 2 more zeros. You do that 8 times, and you get 16 zeros. Now these commas really help me count them. What's inside the parentheses is 10 to the what? Third, just count the number of zeros. 3, 6, 9, 12, 15, 16. And this is equal to, now 10 to what power is 10 to the 16th? We did a practice quiz problem like that. That's 16. 10 to the 16th is equal to 10 to the 16th. Now, that's one way to do this problem. There's a shorter way. You could have also done it like this. $100 is really 10 to the second. And then power to a power multiply. And then you still get the same answer of 16. So there's a couple different ways we could have done this. There's probably more ways, but there's a couple of the more ones that come to my mind. Sasha, does that answer your question? 36?
Yes, and I have one last question for 49.
Go to 49, all right. Without using a calculator, find 2 log of 100 to -3. All right, now the unwritten base, whenever they write 10 log without a base, it's 10. So I'm going to do this the way that I did the second way. I'm going to rewrite this 100 as 10 squared. And then to the -3 power. So that -3 is still there. The 100 has just been replaced by 10 squared. And then this is going to be 2 log base 10. And then power to a power, one base raised at 2 consecutive powers, we multiply. And then this 2 just comes along. This says 10 to what power will give me a result of 10 to the -6. Well, it must be -6. and that's being multiplied by this 2. And then that becomes negative 12. Slasher, does that answer your question there?
Yes, thank you.
You're welcome. Any other questions? All right, that was a nice set of questions. All right, we are at a break time. We will start again. In 15 minutes, which is 1:31 p.m. And does anybody need to speak with me individually before I take my break? All right, see you in a bit. Pardon? Yes, I do know. Okay. 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 That sounds good. What day are you going to do this? Friday? Okay. All right, great. Thank you. Okay, great. Hey, welcome back, yeah. All right, let's start up again. And we are going into 6.5, logarithmic properties. And the first point I need to make is that log functions and exponential functions are inverses of one another. We saw that in some of the problems in the practice quiz, how they cancel each other out. All right, exponential properties are strange. Now, what do I mean by strange? Well, I mean, when I first learned this one, it drove me nuts. There is a multiplication. There's no addition in this problem. And it seems like this multiplication magically turns into addition over here. I mean, you guys have kind of mastered it because, you know, x squared times x cubed, you kind of can visualize x, and that's why it's x 2 plus 3, and it's x to the 5th. But it's still incredibly strange. There is no addition in this side of the equation, but yet you wind up adding the exponents. That, when I first learned that, it was too strange for me. I couldn't handle it. It took me a long time to get comfortable with this. And I remember it was once on a test that I was just like, my mind froze. I couldn't figure this stuff out. But what saved me was visualizing these things and then being able to come back to it. All right, now, the logarithm properties, you might feel like, oh, I got a handle on them, they're not that strange. Well, I mean, the exponential properties you might feel like that. The logarithm properties are going to even look stranger. All right. There's a couple preliminary properties that we're going to do right here. And property A is one of those preliminary properties. And it says log base b of 1 is equal to 0. And then I have this column called y is true. And I'm going to have you go in your groups, and you're going to have to talk it out, and I'll call on a group, and they're going to explain why it's true. So let's just get a quick countdown on groups today. All right, is there anybody here from group 1 today? All right, group 2, I have you folded into group 3. Now hold it. All right, so there's nobody here in group 1. And group 2.
I'm here. Nobody else has responded yet.
All right, are you in group 1?
Yes, my name's Sasha.
Okay, Sasha. Okay, so Sasha, I'm going to put you in with a different group. But let me find out how many are here first.
Okay.
Group 2. So before we do this, I didn't say this out loud. Go into your group chat, type in hi, so everybody knows who's all here in the group. Make sure you know who the spokesman for the day is for the group. Group leader can specify that. Alright, so there's one person from group 1 here. Group 2, how many of you are here?
There's 4 of us here today, Mr. Shankin.
Thank you. Group 3. Yeah, okay. Group 4.
There's 2 of us.
2 of you in group 4. Group 5.
2 here.
2. And group 6.
3.
3. Okay. So
Hi, Mr. Shankin. There's 2 of us in group 1.
there's now 2 of you in group 1. All right. Great.
Yeah.
All right. So we'll leave the groups the way they are then. And all right. So property A, log base b of 1 is equal to 0. Go into your group chat. See if you can figure out why that's true, because when I ask your group to explain it, you got to give me some kind of explanation. So let me give you a minute to go into your group chats, see if you can come up with a reason. Why in the world is that true? All right, group 2. Why is this thing true?
This is. Go ahead, Dustin.
Okay, this is true because anything raised to the power of 1 is 0.
You're close.
Or anything to the exponent of 0 is 1.
That's right. All right. So if we just change to an exponential equation, the base b exponent 0 equals, and then this is the 1 is in the result position, is 1, and this is true. Anything to the 0 power is always 1. And that's what this is basically saying. So whenever you see log base b, let me give you if you see log base 7 of 1, from now on you can always say, oh, well, if there's a 1 there, the result is going to be 0. We don't really refer to this property very much. We just think it through. 7 to what power gives me 1? 7 to the 0 power gives me 1. Okay, but it's still a property. If there's a 1 in this position, in the result position, you always get a 0 for your exponent. All right, next one is property B. It has 2 parts. And I'm going to ask you to explain why it's true. So let me give you a minute in your groups. Okay, group 4. Why is this true?
It's true because the B's cancel each other out and leave the M.
Why do the B's cancel each other out?
I don't know, they just do.
You're right, they do. And they do because they're inverse functions. Boom. And then these cancel each other out, because this is a logarithm and an exponential function combining together. Now, this means they are inverse functions. So y true is inverse functions cancel each other out. Alright, so let's take a quick look at example or two. If I have 2 to the log base 2 of 8, the 2's in the log base 2 cancel each other out, and I'm just going to get 8. It also makes sense because 2 to the third makes 8. So this exponent up here, log base 2 of 8, is really 3. And then you put that on top of the 2, and you're going to get 8. So these things make sense as well as inverse functions, cancel each other out. And let me just show you though what's not the case. If you had log base 2 of 8 plus log base, or plus 2 to the 8, these don't cancel each other out. They have to be inside of each other. There's got to be exponents and logarithms. They have to be kind of intermixed within each other. Then they'll cancel each other out. This doesn't cancel. Okay. Now, these were the minor properties. They were minor properties because they don't get numbers. They just get letters. Property A, property B. We kind of don't really need these properties. We kind of formally put them in there just to remind us that, you know, inverses cancel each other and anything to the 0 power is 1. These are the really important properties. Property, and they get numbers, and there's 3 of them. Property 1. Log base b of m times n is equal to log base b of n plus log base b of n. And this is going to seem strange. And let me show you though that it's no more strange than, remember, x squared times x cubed was x to the 2 plus 3, and it appeared that this multiplication magically turned into addition. Well, because these are inverse functions, something very similar is happening here. This multiplication seems to magically turn into addition. They're kind of related because they're logarithms, the inverse of exponential. So strange things are going to happen here. Similar strange things are going to be happening here. And the way we look at this is, let me just give you some examples before we. So this part, I'm going to do. Suppose I have log base 10. Now the 10 I don't have to write. Let's suppose I just write it in anyway. Of 100 times 1000. Alright. What this property says, now notice that what I've got on the left side is 1 log. There's only one logarithm. Log of this, and I only wrote the word log one time. What I'm going to do in this property is it's kind of like I'm distributing the log base 10 to both numbers. So I distribute it into the first one, and I get log base 10 of 100. Distribute it into the second one, log base 10 of 1000. But when I do that, if I transfer this multiplication sign into here, it will be wrong. Let me demonstrate. So I'm going to do it wrong first, and you'll see why. This would feel like the natural thing to do. I think I'll just distribute this logarithm to both of these things. Now this is 2 logarithms, so very important. I wrote the word log twice. 2 logs. This was just 1. When you write it twice, let's just show what happens. 10 to what power is 100? 10 to the second power. 10 to what power is 1000? 10 to the third power. Now, when I do these over here, let me just go straight down. Parentheses means do me first. 100 times 1000 is 100,000. You get 5 zeros. 10 to what power is 100,000? 10 to the 5th power. So the real answer for the left-hand side is 5. If we put, when we distributed this logarithm to both, if we kept the multiplication sign, we would be getting 6. It wouldn't match. But if we change this addition, this multiplication sign to addition, then we get it to match. And let me further show you another reason why this is true. Let me do this a different way. Log base 10 of 100. 100 is really 10 squared. 1000 is really 10 cubed. Now when I'm taking log base 10 of 10 to the what power? Do I add these exponents or do I multiply them? Ooh, I have to add them. Visualize 2 tens, visualize 3 tens, there's 5 tens altogether. You're going to be adding them here. And that's why we had to add them over here. And so, now 10 to what power is 10 to the 5th? 10 to the 5th power will give me 10 to the 5th. Or log base 10 and 10 to a power cancel each other out. And we get 5. So we see multiple reasons why this is true. But it takes some getting used to. When you try to make 2 logarithms out of 1 logarithm by distributing the log in there, you can only do this in this first case when there's multiplication in between them. And then that multiplication will turn into addition. Like this. Any questions? Alright, now I'm going to give you a hard task for this next one. So this one I kind of did it for you. I kind of gave you an example that showed why property 1 is true. Property 2 is similar to property 1. Instead of multiplication between m and n, it's division. And instead of addition, it becomes subtraction. So that seems appropriate. So now it's up to you to come up with an example that kind of shows with numbers that, oh, this actually works. All right, so I'm going to give you a minute now to work on property 2. And come up with some numbers for these things that kind of demonstrates, oh yeah, this property had to be this way. Just work individually for now. At my cue, I'm going to have you type it into your group chat. And then I'll be calling on a group in a minute. Okay, if you have any ideas, type it into your group chat. Put some numbers. Talk it out. All right, group 6. Got any ideas? Group 6, you can pass if you want to.
I think we'll pass for now.
Okay, let me open up the floor to anybody. Anybody have any ideas? This is not an easy thing. How I might show that this is true with some numbers in here. Alright, let me demonstrate then. And suppose I used log base 2. Then I'm going to put two numbers that are going to divide. But I'm not going to put numbers like 5 and 3. I'm going to put numbers here that, because look at what I did over here. The base 10, and this was 10 to some power, and this was 10 to some power. So this is base 2. Let's do 2 to some power and 2 to some power. Let's make it as simple as we can. 8, because that's 2 to the third, and 4, because that's 2 to the second. Alright, now let's go and we're gonna, now notice this is 1 log. On the right hand side we're going to make 2 logs out of this. When I make 2 logs, you distribute this log base 2 to this one. Now there's a division sign between, so I'd be awfully tempted to put a division sign here. But if I do, I'll be wrong, and let me show you. So distribute this logarithm to both, we'll get this. Alright, now let's work on the left hand side let's just go straight down. 8 divided by 4 is 2. This asks 2 to what power is 2? 2 to the first. This one. Log base 2 of 8 says 2 to what power is 8? 2 to the third is 8. Now if I kept this as divided by, 2 to what power is 2? 2 to the second power is 2. Now if I did 3 divided by 2, I'd get 1.5, and these are not equal. What did I do wrong? I used division. I have to change that to subtraction. This division sign, when you make 2 logarithms out of 1, the division sign changes to subtraction. I told you these properties are strange. And this becomes this, and then we get a 1, like this. Only if this thing magically changes from division to subtraction does it work. If I keep it as division, I get the wrong answer. Alright, so this has kind of been a bit theoretical here, and these properties are strange. Give me a little feedback. Are you hanging with me, or do you need me to go over this again, review this basics again, or you got it, and can I move on to the next part? So everybody just quick check in here. Okay, this will take lots of practice. These properties are really strange. Okay. Now let's come back. Alright, so we have property 1 and property 2, and they're quite similar. It's with multiplication and division. And then property 3 is even weirder. And let me give you an example that kind of demonstrates why it's true. Now what this property, first of all, is saying is that when you take log base b of m to the r, that this r gets to move out into the front right here, and you get r times log base bm. Now this might seem strange, but it's not really that much stranger than this. 2, well, hold on a second, x to the second to the third power. You guys are confident that this is not x to the fifth, but x to the 2 times 3. Which is x to the 6th, not x to the 5th. Now what this is saying in the world of exponents is power to a power, you multiply. And this is going to wind up doing that because the logarithm itself, a logarithm, is an exponent. It's a power. So you're kind of taking a power to a power when you're doing right here. And that's going to wind up turning it into multiplication. So, as crazy as that rule is, because this one is really, I mean, you'd expect 2 to the third is 8. I'd expect an 8 up here. But no, you just multiply these things. And here, well, you wind up just multiplying. So, let's take an example with this. Let's take log base 10 of 100 to the 5th power. Now, let me apply this rule directly. If I use this rule, it says this number gets to come out front. And I would get 5 times log base 10 of 100. And this is 5 times, well, 10 to what power is 100? 10 to the 2nd power. So this is 10. And the reason why this is true is, let me show you. If I come straight down here, this 100 is the same as 10 to the 2nd. And this is log base 10. Power to a power you multiply. 10 to the 10th power. 10 to what power is 10 to the 10th? It's just 10. So we see we're going to get the same answer on both sides. And there was going to be a kind of a power to a power multiply thing here, and that's what winds up happening. The logarithm itself is the exponent. A logarithm is an exponent, and then that gets raised to another power. Alright, so these three properties are strange, but really important properties. We're going to be getting to where we're solving exponential and log equations, and you have to have these properties mastered to be able to do those problems. So we're going to get into the next few sections are probably the hardest sections that we're going to be doing all semester. But they're crucial sections. For instance, if you are going to take chemistry, one of the chemistry courses has a prerequisite of college algebra, and the reason why it has a prerequisite of college algebra is because it has logarithms in it, and students have to be able to work with logarithms in there. And when you go into other, even in business and in science, logarithms show up fairly often. Alright, that's property 3. Then there's what's called the change of base formula. So there's 3 main properties, 1, 2, and 3. And then this one is so important, it doesn't get a number, it gets a name. Change of base formula. Now remember, on the practice quiz, I gave you this problem. Alright, now pull out your calculator with me, if you've got one with you, and do this for a second. Go 3 raised to the 1st power, and it's too small, it's 3. 3 raised to the 2nd power. Let me go to my document camera. Okay, so put my calculator in here so you can see. Maybe it's better with this line out. Okay, 3 raised to the 1st was 3. 3 raised to the 2nd was too big, 9. 3 raised to the, I want to get 7, because 3 to some power is 7. 3 raised to the 1.5 is not big enough. I want to get 7. So 3 raised to the 1.7, let's say. I'm getting close. 3 raised to the 1.8. Trying to get a result of 7. It's somewhere between 1.7 and 1.8 is what I'm looking for. So let me take this away. Close that out. So this is somewhere between 1.7 and 1.8. But I can get it really precisely in my calculator if I use this formula. Now, the strange thing about this formula is that on the left-hand side there's only 2 letters, B and M. On the right-hand side, there's the same 2 letters, B and M, but a new letter A that didn't appear in the left-hand side. That's really strange. Not many formulas are like that. And when a new letter just appears out of nowhere, it means you can pick it to be whatever you want it to be. And we usually pick A equal to 10 or A equal to E. Now, let's pick A to be 10 right now. So this is going to be log base 10, because we're picking the A to be 10, of M. Now, look at these two numbers, 7 and 3. I think the 7 is closer to the ceiling, and the 3 is closer to the floor. This one's higher up than that one. The one that's closer to the ceiling stays closer to the ceiling. The one that's closer to the floor stays closer to the floor. This is how we use this formula right here. Now, most calculators only have 2 bases for logarithms available, base 10 and base E. That's why we choose our A to be either 10 or E. So now I'm going to punch these out in my calculator. I'm going to put log 7, and I got 0.8445098, keeps going, and then log 3, I got 0.477121, keeps going. Alright, so this one, log base 3 of 7, that was a practice quiz problem. And we had said, oh yeah, right here, that we can't do it. But I had underlined yet. Can't do it yet. Now we are able to do it. So now I'm going to put, actually I usually don't write these numbers down. I usually jump right from here right to my answer. And I'm going to punch it in again. I'm going to put log of 7 divided by log of 3. And I get 1.177,124, so on. And now I get this result. And what I'm going to do, I'm going to put my camera here. I'm going to take 3 raised to that 1.77124. Now I'm not putting all the digits in there, so I'm not going to get exactly 7. But look how close I get. I get really, really close. This, if I'd have put all the digits in, I'd gotten even closer. Alright, so Let me That's the change of base formula. It allows you to change to whatever base you want. If you go to base E, then we call them ln. ln7 over ln3. All right. So I'm going to quickly go through these because you need to understand the directions for the problems that you're going to be doing. So let's do problem number 5. The directions in your textbook, and this is the actual problem 5 in the homework. For the following exercise, expand each logarithm as much as possible. When you see the word expand, it means write many logs from 1 log to many logs. So I'm going to write, instead of 1 logarithm, I'm going to distribute this log to both. And then it's a division sign. I'd be tempted to put a division sign here, but that would be wrong. Instead, it should be a what? A subtraction. It's going to be log base B 17. That's it. When you expanded it, rewrite each sum difference as or product of logs. You change from 1 logarithm to more than 1 logarithm, to as many logs as you can. Okay. And when you see condense to a single logarithm, oh, by the way, what property did I use for this? I use rule 2. I like to write the rule number right above the equal sign. I used rule 2 or property 2 right here to do that. Okay. For the following, condense to a single logarithm. Okay, let's take number 12. I'm going to put these 2 together because you only do 2 at a time. You can't do all 3 all at once. This is ln. Now, what property am I going to be using to go from here to here? I'm going to be using property 2 again, but I'm going to be using it in the reverse order. A divided by T minus ln C. So what I did to go from here to here, I used property 2. Let me show you. Property 2, I used it in this direction. I took 2 logarithms and changed it into 1, and the subtraction changed into division. That subtraction right here changed into that division here. Now I'm going to use that property again. And I'm going to make ln, oops, of this divided by this. I'm going to put the C over 1. And that's the same as ln. Copy dot flip. And I'll put them in alphabetical order. A over CD, like this. So that is what it means when it says condense. I took 3 logarithms and I got my final answer as 1 logarithm. Condense means multiple logs go to 1 log. Okay, and I know I'm over time. I'm gonna do a real quick example here on 25. Rewrite as equivalent ratio of logs using the indicated base. I'm going to say that that is equal to, I can choose whatever base I want. It says to choose base E. And then the number that was higher up, closer to the ceiling, stays higher up. The number that was lower stays lower. But this can be rewritten as ln 15, that's the typical way, over ln 7. Okay, so that's, then you could punch it into a calculator. You can't punch this one into most calculators. Most calculators only have base E, ln, or base 10 log. Okay, and alright, I'm going to leave the rest for y'all. I think I've got through enough to get you to the basics. So the homework is 6.5. And let's briefly talk about what's coming up. Today is the 19th. Next week, on Thursday, there's no class because of Thanksgiving. The week after that, there is exam 3. And then in the week after that, you'll have your final exam. For exam 3, there's going to be a practice exam posted, and you'll be able to find that in the modules, and you can work on that to get you ready for that exam. All right, any questions? All right, we'll stop here, and I will stop the recording.